Hello students, in this video we're going to talk about end behavior of a rational function. So you can kind of imagine there are several possibilities of how a rational function would behave when x is very large or when x is very large negatively. That's what we mean by end behavior, is when x is going to positive infinity or x approach negative infinity. So one scenario is that the function simply increases or decreases without bound. In other words, it doesn't approach a finite value. So here's an example. Let's say f of x is a rational function. Numerator is x to the fourth power plus 1, and the denominator is x squared plus 1. And you can see that the numerator is going to keep growing a lot faster than the denominator. So as x approach infinity, f of x is also going to approach infinity. It just keeps growing. Okay, so that's scenario number one. Okay, the second scenario is that the function approaches a finite value. So let's say my function is f of x equal to 1 over x squared. It's still a rational function. The denominator is second degree and the numerator is 0th degree. And as x approach infinity, you can see that f of x approaches 0. Right? So as x goes to infinity, f of x approach 0. And in fact, it's the same on the other side. In either case, f of x approaches 0. And yet another scenario is that the function actually approaches a non-zero value. So an example is f of x is equal to 1 plus 2x over x. And as x goes to infinity, f of x approaches 2. And the last possibility is that it actually approaches a line, okay, y equal to mx plus b. So in this case, I'm not giving you the function, but let's say I have a function as described in this graph, and as you can see, as x approach infinity, then f of x actually approach the equation of this line here, okay? Let's just call this y equal to mx plus b for now, okay, with slope m and y-intercept equal to b. And we'll examine this in detail, okay? That these are not the only scenarios for end behavior. There are other possibilities, but for the purpose of this class, these are the 4 scenarios that we're interested about. Okay, so how do we identify these different scenarios based on the given function? So that's what we're going to talk about next. To examine the end behavior of a rational function, and here I've written it as f of x is equal to p of x divided by q of x. So p is in the numerator and q is in the denominator, and both p and q are polynomials. It's really the comparative degrees of p and q that would determine the end behavior of f of x. Okay, and we can break it down into several cases, and then we can look at those one by one. The first case is when the degree of p is 2 or more larger than the degree of q. So if you take the degree of p as a number and subtract the degree of q, if that number is greater than or equal to 2, then f of x is going to increase or decrease without bound. And here's an example. So what happens if, in the case of this function, as x goes to infinity, the dominant term in the denominator is going to be x squared, and the dominant term on the numerator is going to be x to the fourth. And x to the fourth is going to grow so much faster than x squared that the function is just going to keep growing. So it's going to increase without bound. And let's say if I were to put a negative sign in front of the x to the fourth, okay, similarly, the numerator is going to grow negatively so much faster than the denominator, and the function is going to decrease, keep going to negative infinity without bound. So in either case, the function does not have a limit that is approaching. Okay, so that's scenario number one. Again, when the degree difference is greater than or equal to 2. Next, we can have the degree of P minus degree of Q equal to 1. This is a very interesting case, so I'm going to defer that until later. And let's keep going. The third case is when the degree of P minus degree of Q is exactly equal to 0. In other words, it's the same degree of polynomial in both the numerator and denominator. In this case, f of x is going to approach a constant value. In other words, it will have a horizontal asymptote. And here's an example. Okay, so let's say I have such a function. As you can see, the numerator has a third degree polynomial and the denominator is also a third degree polynomial. And as x approach infinity, the dominant terms are going to be the one with the highest exponent, right? So in the numerator is 3x cubed and the denominator is x to the third power. So that can be simplified to be 3x to the third divided by x to the third. Okay? And these two will approximate each other out as x goes to infinity. And eventually, this is going to approach the value 3. So it would have a horizontal asymptote at y equal to 3. And the last case, case number 4, is when the degree of P minus the degree of Q is less than or equal to -1. In other words, the denominator is going to be 1 degree or higher than the numerator. And here's an example. And let's say I have this function, and the numerator is a second degree polynomial, but there's a huge constant. The constant is 10,000. And in the denominator, I have x to the third plus 1. Well, as x goes to infinity, regardless of how big this constant or the other terms are, the dominating terms are going to be the leading terms with the highest exponent. And because the denominator is growing to the third power, it's just going to grow much faster than whatever the numerator is. And as it approach as x approach a very large value, f of x is going to approach 0. And if the denominator has an even higher degree polynomial, it's going to grow even faster, and therefore it would approach 0 even faster. So in all this scenario, f of x is going to be approaching 0. And that's case number 4. And lastly, let's talk about case number 2, which we skipped. Case 2 is when the degree of P is exactly 1 degree higher than the degree of Q. Okay? And in this case, f of x would actually approach a linear equation, what we call a slant asymptote. And let's see how that works. And in this case, we have to be somewhat cautious, and I'll explain why. So if we use the same logic as we had before, given these functions, 6x squared plus 3x plus 7 in the numerator and x plus 1 in the denominator, as x approach infinity, we might be tempted to say, well, as x goes to infinity, then the dominating terms in the numerator is 6x squared, and the dominating term in the denominator is going to be x. So therefore, f of x would approach 6x squared divided by x. And this is going to be, since x is becoming very large, I can cancel out one of the x. So this is going to approach 6x. And that would be wrong. And we'll see why in a minute. So we have to be using a different technique to analyze a slant asymptote, specifically in this situation. So here's what we do. Instead of just looking at the leading term, because the degree difference is just 1, we'll go through a long division to find out exactly what the slant asymptote equation is. So here's what we do. Okay, so I've erased the wrong information or the wrong approach, and I rewrite the rational function. And this time we're going to do a long division, okay, dividing the numerator by the denominator. And you remember how to do long division from one of the earlier videos. So I'm going to divide x plus 1 into this expression here, and in order to satisfy my first term, I'm going to need to multiply by 6x, right? So this is going to give me 6x squared plus 6x, and then I'm going to do a subtract. This one goes away, and I'm left with negative 3x for my second term. And then I'm going to pull down the 7. All right. Now I need to do the second step. So x times something is going to give me negative 3x. So multiply by negative 3. That's going to give me negative 3x, negative 3. And then I subtract again. So again, the first term drops out. 7 minus negative 3 would be 7 plus 3, which is 10. And that's my remainder. So I can rewrite this rational function that I'm given as a quotient plus an error term. And the quotient is 6x minus 3. And the error term would be the remainder over the original denominator, right? Recall from some of the earlier videos. This is what we call the error term. And now it becomes clearer where the asymptote is going to be. Because as x becomes very large, what happened is f of x is going to approach, 6x minus 3. This whole expression here, okay, it's going to approach this. Because the error term is going to drop out. As you can imagine, when x becomes very, very large, then this whole fraction is going to be 10 divided by a very large number, which becomes less and less, so it's going to approach 0. And if you plot out the function using decimals, this is what you see. The function is in purple. This is f of x. So as you can see, as x approach a very large number, it gets closer and closer to this asymptote. And similarly, on the negative side, and when x approach negative infinity, it gets closer and closer to the same asymptote. And the equation of that asymptote is y equal to 6x minus 3 with a slope of 6 and a y-intercept of negative 3.